Hi there, I'm Dr. Ben Raymer, President ad interim of UTMB in Galveston. Our institution is honored and thrilled to sponsor the Thought Leaders Lecture Series. As an academic medical center that provides comprehensive, high-quality, and accessible care across the entire Bay Area and down into Galveston, we are proud to partner with Space Center Houston to bring you these stimulating talks featuring some of the best, brightest minds of our time, sharing their views on a wide variety of complex scientific topics. While the COVID-19 pandemic continues to unfold and dramatically change our daily routines, teams of individuals across our institution are working to counter the virus on all fronts. We're caring for those impacted by the disease, testing those who are sick or who have been exposed, and working hard in our laboratories to better understand how this virulent threat behaves. We hope that these engaging and educational lectures provide you a needed respite during these trying times and serves as a reminder to you that humans have the capacity to do great and brilliant things, even in the face of adversity. Thank you and be well.
Greetings from Space Center Houston. My name is William Harris, President and CEO, and I'm delighted to welcome you to our first Virtual Thought Leaders Series program. Today, we're going to be focusing on evidence of human presence on the International Space Station. Through this series, we provide you an opportunity to participate in the conversation through submitting questions, and people have done that in advance. Space Center Houston really strives to create a community of problem solvers and fuel the STEM pathway to advance a science and engineering literate community and society. We're the official visitor center for NASA Johnson Space Center. We feature over 400 artifacts that interpret the past, present, and future of space exploration. We are a dynamic learning destination, and we look forward to welcoming you back in our doors in the very near future. But meanwhile, we're delighted to bring you this very exciting program. We'll be moderated today by our scientist in residence, Dr. John Charles. John has a 33-year distinguished career at NASA as the chief scientist in the Human Research Program and has many other achievements to his credit. We're so delighted that he's now part of our team and is going to be leading the discussion today with our distinguished panelists. So without further delay, I'm going to turn it over to Dr. John Charles.
Good. Thank you very much, William. What a pleasure it is to be here today as part of this panel. This is, as William mentioned, our Thought Leaders series for 2020, and this year being the 20th year of habitation, continuous habitation of the International Space Station. We're trying to put special emphasis on humans inhabiting the space station and humans in spaceflight in general. When we chose the title for today's presentation, Evidence of Human Presence on the International Space Station, it was admittedly tongue-in-cheek because space stations are only space stations if there is human presence on board. If you see a space station, you should expect to see humans. So now we're talking about looking at a space station and deciding how we can tell if there is human presence on board. Luckily, we have two I think world-class experts on the topic that can walk us through the discussion. We're very fortunate today to have Dr. Gary Kitmacher and Dr. Jack Stuster here as our subject matter experts. One of the benefits of having a long career at NASA is a chance to work with stellar individuals like these. Jack Stuster, who you're going to hear from in a few minutes, is a well-known researcher in the area of human factors and human performance in space. And I had the good fortune to get to know Jack when I was when I was a chief scientist and he was one of our investigators. We enjoyed working with Jack so much that after his first investigation wrapped up, we liked it so much that we asked him to do it all over again with a second group of astronauts. That's almost unheard of in the NASA business, being invited back for a twofer. So that tells you how highly we valued Jack. Before we hear from Jack, we're going to hear from Gary Kitmacher. Gary and I go way back. He is almost as big a space nerd, and that's probably questionable. If you can tell by the background in his office, he's got many models of rockets. But he and I do enjoy engaging in space trivia discussions and so forth. Gary Gary was the architectural control manager for Space Station Manned Systems, and he was involved in the Russian Space Station Mir activity as the manager for the NASA Mir re-outfitting of the Peroda research module. He also worked on space shuttle stowage and crew equipment and was utilization planning manager for several of the SpaceHab commercial space shuttle missions. He holds a bachelor in science, geology and geophysics, a master's, an MBA, and a doctor in education from the University of Houston. And getting back briefly to my colleague Jack Stuster, he's a certified professional ergonomist. His work with NASA began only recently in 1982, so he's a newbie. With analysis of space shuttle refurbishing procedures, he was the guy walking around telling the engineers, why are you doing it that way? There's a better way to do it. He developed design and procedural recommendations to facilitate sustained human performance on the International Space Station and future spacecraft and at planetary facilities. He has contributed immeasurably to the training program of the Expedition Corps of astronauts specifically assigned to the long-duration flights. And I think most importantly and most pointedly for this discussion, he contributed he conducted content analysis of the confidential journals that were maintained by astronauts during their expeditions on the International Space Station, which documented 11 person years of living and working in space. Jack noticed early on that the astronauts were often writing diaries, keeping diaries of their time on the space station. And the rest of us, I think, noticed it as well. We all sat around and say, gee, it sure would be fun to see what the astronauts are writing about. Jack said, well, leave it to me. And he came forward with a proposal that won the astronauts' confidence so that he was allowed to see their diaries without revealing any personal information. And by encoding it usefully, he was able to tell the rest of us what the astronauts were happiest with and most unhappy with, as well as protecting their confidentiality. We're going to hear more from Jack about that, but first I'd like to have Gary Kitmacher give us his perspective on the space station, how it got to be the way it is, what it takes to design a space station, and so forth. Gary, can you take it away?
Okay, thank you, John Charles. I have been involved in the space station program since about 1985-86. Got fully immersed in it as the Challenger accident investigation was wrapping up in '86, and was part of the Manned Systems Division. We prided ourselves on designing the insides of the space station, especially for the flight crew. So that's mainly what I will be talking about today. This is an artist rendering by Chesley Bonestel back from the 1950s. At the time, Wernher von Braun was popularizing the idea of this donut-shaped space station. You also see a space shuttle and a space telescope in this view. The wheeled space station was not something invented by von Braun. That went back to the 1920s. And the whole concept of a space station living in space can really be traced back to the beginnings of the Renaissance, to the famous astronomer Johannes Kepler, who wrote about a space mission and about the people who would sail these new ships in space. If we go to the next slide, we can see the space station as it was depicted about the time that I was first involved with it in early '86. And we see the space shuttle, the Hubble Space Telescope, and the station at that time was called the dual keel. Not only do you see a station that's somewhat larger than our current ISS, but you even see on board a big hangar, which is where we were going to prepare for our lunar and Mars missions. We were going to prepare a series of spacecraft to depart from the space station. This is the large diameter space station. Until about 1969 or 1970, NASA was thinking this is what a space station module would look like. It would be launched by a Saturn V rocket. Saturn V had a diameter of about 10 meters, 33 feet, and therefore that's how large this module was. But in 1969, they basically turned off the assembly line for assembling the Saturn V's, and it went instead to the space shuttle. And so we thought at that point our modules would have to be a lot smaller. Now, we had been thinking about different space stations. We were planning one called the Skylab, but when the Russians failed to land on the moon in 1969, they decided instead to put up a small space station. And we can take a look at this film clip, which shows the Salyut space station, designed by the Salyut Design Bureau, which was at that time part of the Energia company. And here it is, launched by a Proton rocket, the largest rocket that the Russians had in their inventory. The Salyuts were single module space stations, quite a bit smaller than our Skylab, which we'll talk about in a moment. Different rockets with the Soyuz capsules on board would service the space station. And the first crew stayed a month, did not survive the trip. I'll get into that later, perhaps, if we have time. But this was life on board the space station. It became familiar to Soviet citizens as they were broadcasting TV down across the country every evening. They did a variety of different kinds of scientific and military experiments. They experimented with showers and with different kinds of living quarters. Towards the end of the Salyut program, on Salyut 6 and 7, there were a series of larger modules that were brought up, and the Russians perfected a method of using a robotic arm to move the additional modules off to right angles. And on the Mir space station, which was launched in '86, this was somewhat perfected with a whole series of additional modules. The Russians brought up a variety of international guest visitors, and in 1995, the U.S. shuttle began to visit the Mir space station. Here's the shuttle Atlantis coming up on STS-71 for the first mission to the Mir. And here's Hoot Gibson and the Russians opening their hatch. We had an astronaut spend several months on board the Mir at this point, Norm Thagard, who is in this view riding the bicycle ergometer in the main crew cabin area of the Mir. Unfortunately, Norm's experiment module called the Spectre did not arrive until very late in his stay. One of the things we discovered about Mir was it was somewhat past its lifetime. It was planned for a 5-year life. By the time Norm got up there, it was about 10 years old, and it would continue working in about another 5 years until it was 15 years old, but many of the systems were breaking down. Here you can see both shuttle and Mir cosmonauts and astronauts together. We did a variety of scientific experiments, including human biology experiments. The Russians were engaged much of this time in maintaining the station, doing different kinds of repair work. And on STS-71 in June and July of '95, we brought a Spacelab module up to the Mir so we could carry on the science over there. Here, the cosmonauts are planning a fly around to take a picture of the shuttle as it leaves. This is one of the things we learned about how the Russians operate, whereas we like to do things very methodically, very thoroughly. The Russians thought nothing of hopping in their Soyuz, as you see here, maneuvering out away from the Mir and taking this picture of the shuttle as it undocked from the Mir on July, I think, 4th of '95. And then in this next view, we see the Soyuz with the cosmonauts coming back to rejoin the Mir station. The shuttle carried on for another couple of days. This is the view of the Atlantis with the Spacelab in the payload bay. And coming up from the tunnel of the crew cabin of the shuttle into the Spacelab module served as a model for what we thought space station modules should look like. Racks on either side, a floor and a ceiling, a lot of the supporting systems in the floor and in one end of the module. Here you see some of the human life sciences experiments. Now, going back to the time of the beginnings of the Russian program, first they started with Salyut, and we had the Skylab space station. Skylab was based on the third stage of a Saturn V rocket. The third stage was somewhat narrower in diameter, so it wasn't that large diameter module that I had shown a few moments ago. It was about 22 feet in diameter, still quite a bit larger than the Salyuts that were typically 12 to 15 feet in diameter, with a lot of equipment, so it filled up, and the aisleway was often no more than just a few feet across. And if we go to the next slide, you can see a picture of the interior. Here is the Skylab in orbit. There were 3 crews of 3 astronauts. This is going from the narrow end of the station, the multiple docking adapter. And then this is the view from the large workshop area. Very wide, very open. The Skylab station had a couple of main work decks. Here you see the living quarters, the bicycle ergometer. Here's John Charles's favorite experiment, lower body negative pressure. The astronauts loved running on these water tanks. The ground controllers not so much, because it made the station difficult to gyroscopically control. So instead they would string this long handrail. It wasn't a rail, it was really a strap, and they could do acrobatics without bothering the outside of the spacecraft. Here's a handball game, Joe Kerwin on the first crew. The astronauts hated the idea that in some compartments, like this is the Apollo telescope mount control station, were at right angles to other parts of the station. They wanted a consistent orientation. The astronauts loved to do useful scientific work. For instance, using that Apollo telescope mount, they would look at the sun. They would perform different kinds of technological and scientific experiments. They had living creatures with them. This is Arabella the spider spinning a web in zero gravity. They had Earth resources photography experiments where they would take pictures of different scenes on the Earth. And they had a large 20-inch diameter window, which they enjoyed looking out the window. They had a shower that was more trouble than it was worth, a galley, food warmers, and the galley table. And this is an overall view of the main workshop area of the station. Go ahead to the next slide and we'll see what we decided about the time that the shuttle was approved in 1972, what the station might look like. And that was, it would be a modular station with the smaller modules carried up inside of the payload bay of the shuttle. This evolved somewhat by the late 1970s. Next picture, we can see the Space Operations Center, which was the Johnson Space Center's favorite idea of what a space station might look like, made out of these small modules. In this case, they were connected together by tunnels. Some of them, on the other hand, had modules connected the side of one module to the end of another. Let's go to the next slide and I will show you what our organization looked like. Manned Systems was one of the so-called distributed systems of the station. It was recognized just like the environmental control, data management, and other systems. It was placed in the Space and Life Sciences Organization because the top managers, Christopher Kraft, Max Vauger, felt that the station would not be adequately designed if they left it in the engineering organization. And so we kind of operated out of a different organization, perhaps a little bit different mentality. We were actually placed at the top of the pyramid. So we would define the requirements, and other systems had to make sure their systems were sized to support what we said that we needed. And if you go to the next slide, you'll see the station called the Power Tower, which once the station was approved within a fairly short time, this is what it looked like. And if you take a look at the modules, they're down at one end of the station, and they are linked together. These were the so-called common modules. All the modules were essentially the same, and they had series of hatches around the periphery towards one end, and then a hatch on either end of the station. And that's what we started with in early '86. We very quickly evolved away from this configuration. This is the plan. Almost from the very start, we were working with the internationals, with the Japanese, the Europeans, and the Canadians to design the station. This particular plan was laid out probably in 1987, and it shows what would eventually become the nodes, and along with the larger modules of the station. This is an interim version in which we had spherical nodes connected by narrow cylinders, which we called tunnels. And so we were looking at the different module configurations and how they should go together. You'll notice that the station was organized in what we called a racetrack. So it was a closed loop. And this was because the station had to have a safe haven ability. The requirement was defined that we could lose any one module of the station, and we would have to have enough equipment and enough systems operability to maintain a crew until a space shuttle came up to visit. That was how we defined it initially. This was our organization within the Manned Systems Division, looking at the design of the station. We had a number of subsystems, which were based on the subsystems that we had previously had within the space shuttle program. We had a central design team that was looking at the overall architecture, the requirements, the interfaces to other systems, and then we had management overseeing what we were doing. As we were looking at the common module, this was one version of the common module, and by the way, it was called that because it was envisioned that we would be turning these modules out kind of like a sausage is turned out in a sausage factory, or kind of like airliners are built. You know, the Boeing airliners in particular, they build lengths of fuselage and they cut them off at a certain length depending on whether the airplane is a 717 or a 727 or a 737, and then they will put a nose and a tail on it. But we were envisioning we could build our modules in the same fashion. This particular idea was called the bologna slice, and it was divided up similarly to the main workshop of the Skylab, with floors going perpendicularly compared to the length of the module. We mocked this up, which you see in this next picture, in full scale, and everybody hated it. Let's go to the next slide. Because all of the compartments were very small, there were no open areas, and so we got away from the bologna slice model very quickly. We had a variety of companies and universities involved in the design effort, and so the next few come from some of those other outside organizations, showing the a longitudinal layout. This is with equipment laid out along the walls of the module. We found that this was not very good because you did not have adequate space to put all of the equipment in. So then we started looking at how to repackage the equipment in the next slide. This is called the loft, and the equipment was placed into modules, into racks that would line the walls and floor and ceiling. There were some open areas, which you see here. Next slide had we were looking at how do you run utilities throughout the module and throughout the station. So this version, called the center beam, had utility runs running through the length, and then the packages of equipment, the racks, would be mounted on that center beam. And the next slide shows the floor center utility run. So here the floor became the main way for the utility runs, and then equipment was laid out in between. We evolved eventually to this next configuration where we had racks of equipment, and we had utility runs originally in just one plane, or later in two planes. Here we have two different sizes of racks, smaller racks on the ceiling, larger racks to the side, and we then evolved to what we called the standard rack. You can see our first mock-up of the standard rack configuration. So all the racks that line the floor, the ceiling, and the walls were essentially the same dimensions, and the utility runs would run through the four corners, which we can see in the diagram. So you see the four corners with the utilities, the racks placed in between. One of the things that this allowed was multiple areas for the utilities, so we could run the air conditioning. So for instance, air would come out of the ceiling, the intake would go into the floor area. We could put plumbing all along there. We could standardize the plumbing. And very important, because we were concerned about micrometeorite or orbital debris hits, if we ever had to gain access to a pressure wall, we could pull a rack out away from the wall. And we could also move the racks around. So everything was very modular, even on the inside. Let's go to the next slide. You can see a test that we did with a fully pressurized shuttle spacesuit EMU, and you see the base of the rack pulled out away. You see one of the corner standoffs, and so even if the astronaut had to go into a depressurized module in a spacesuit, they would still have pretty good access to virtually all areas of the pressure hull. And if we go to the next slide, you can see on one of the first increments, the astronauts actually delivering the racks inside of the US lab module. It was quite interesting after years of planning this out and defining the requirements and defining the design to go to the building at Marshall Space Flight Center in Alabama, where a couple of technicians were actually laying these racks up by hand. This was a carbon fiber to reduce weight, and so they made all of these racks by hand. We were also looking at how large these racks needed to be so that people could actually get inside of them. And we were designing the station for everything from a 95th percentile American male, which is what you see here, to a 5th percentile Oriental female on the smaller side. These units where the people had to be able to get inside were called functional units. And in fact, they would become the basis for things like the crew quarters. We were also in the late 80s looking at how Russians were doing things. And so we were looking at how the Russian crew quarters were arranged on the Mir. This is actually on ISS on the first increment. but the mirror was essentially the same. And you notice in the Russian crew quarters, they have windows, and we had intended to have windows, but we would fairly often battle with the engineering and management. For instance, they ruled windows were too expensive. The mechanical engineers felt windows were a point of weakness, and so we never got windows in our crew quarters. Next picture, we can show a mock-up of one of the crew quarters with one of the windows in it. This is in our first full-scale standard rack configuration of the station. And then if we go to the next slide, you can see the actual crew quarters on board the station today. And you can see how they are organized on floor, ceiling, and both walls. So the astronauts actually sleep around in a circle. Next picture, we looked at how different kinds of equipment. This is a microgravity glove box being packaged into a rack. And we had a simulator where we could actually plug these racks in. Everything was intended to be very modular, very standardized, be able to move the racks around the cabin at will almost. And in fact, we have used this capability on the station. Originally, when the US lab went up, it was filled up with equipment. As soon as the Japanese and the European labs went up, a lot of the equipment was moved out of the US lab and into the European and Japanese labs. Here you can see the way in which in the early 90s we envisioned the modules were going to be organized. There were supposed to be both a HAB module and a lab module. In fact, we did all of our design work looking mainly at the HAB module and thought that the lab module would be essentially the same thing, but for scientific equipment. You can see some drawings of how the equipment is arranged on the inside. This is for the lab, and the next picture shows for the HAB. And in fact, both module shells were built. And if you go to the next slide, you can see the HAB and the lab being manufactured at the Marshall Space Center in Alabama. But ultimately, the HAB was canceled in a cost-saving measure, and so we only got one of the two large modules. And the next slide shows the US lab in orbit. And I'll just talk about a couple of the smaller subsystem areas. We looked at how computers and the human-computer interface would look. If you go to the next slide, we envisioned computers would be in full racks. Keep in mind, in the mid-1980s, when we were doing this work, laptops weren't invented yet. Here's a full-up, mocked-up computerized rack. This is what we envisioned it would look like. One of the discussions I had with some of the architectural folks was I thought that the astronauts would want to look out and see through a window either docking spacecraft or spacewalking astronauts or the assembly of different modules of the station. I based my requirements on how the shuttle operated. In fact, this particular picture was really the basis for the requirements that I established. And ultimately, we did get a module that provided this kind of capability, which I'll talk about in a moment. But the module didn't arrive until the very end of the assembly phase. And so most of the work of assembling the station was done from workstations that look like this on the interior of the module, particularly the US lab, using a lot of individual screens. We'd gotten beyond the CRT, and so we had flat screens, we had hand controllers, we had laptop computers, but we had no windows. And so the astronauts often could not really see what they were doing, at least during the assembly phase of the missions. The only big window that we had through most of the assembly phase, you can see the 22-inch scientific window in the US lab module. Now, as I say, I was basing the original requirements on how we operated in the shuttle, particularly the aft flight deck of the shuttle. You can see the one of the first models of what became known as the cupola. At this point, I was still calling it the windowed workstation. We didn't come up with the name cupola until some time later. We mocked it up full scale in the next slide in PVC and did some underwater tests. We were all about being able to put multiple people, computers, and a full immersion cupola. The astronauts would be able to stand up inside of it, essentially. You can see a full-scale mock-up of it. Laurie Weaver on the right side in this picture, who had started out as, I think, a student intern with us, was really doing most of the actual design work of the cupola. Here you see we're working with a number of our Japanese visitors, including one man, Shiraki, who became the Japanese program manager and who is still involved in the program today. But this was the octagonal full immersion cupola that is what we preferred. We were looking at other configurations that were shorter, that were hexagonal in shape. Next picture, we can see a full-scale mock-up with the computer equipment on the inside. Again, this is before the laptops. And then the next slide shows the cupola that we actually wound up with. And the next series of pictures actually show the cupola in orbit today. There were supposed to have been two cupolas, one on top looking forward and one on the bottom looking back. We only wound up with a single one of them, unfortunately. And the last area that I'll talk about, because it gets to a little bit towards future designs, is inflatables. We talked all through the design phase about the idea of using an inflatable. And after I got done with my design work on the space station, I went off to support the first President Bush's space exploration initiative. And so this was the design that I developed and piece of artwork that I did showing an inflatable moon base. And we actually tried, other people tried, it was not me so much, tried to actually build this in full scale at the Johnson Space Center, and they could not figure out how they would ever get it there and set it up. And so instead they developed this next configuration that you can see a computer graphic of called the Transhab. And in this configuration, the inflatable was folded down along the center core that would contain all of the utilities and all of the equipment. And then once it was up in space or on the moon, it could be inflated and you could maintain the center core with all the equipment. They actually did mock this up in full scale and actually inflatable. If you see the next slide, you can see the inflatable inside the thermal vacuum chamber in Building 32 at the Space Center. And JSC designed all of this, patented it, and then sold the patent rights to Mr. Bigelow, who subsequently set to work to actually build a series of these modules, several of which were placed in orbit, and one of them is attached today on the space station. And so that's all I have for you today, and I'll be happy to answer questions.
Thanks very much, Dr. Kitmacher. That's a great perspective. That's a great overview of how we got where we are today and some of the design considerations that you and your colleagues worked through to make the space station into a reality. What I'd like to do now is segue a little bit to Jack Stuster and have him talk to us a little bit about how it's actually working out for the operators. Jack, you have a unique perspective. You have a privileged position in as much as you get to hear or at least read what the people that live aboard the International Space Station say about it during the times that they're trying to fit in and make things happen and make things work. And do they ever complain about Gary Kitmacher, let's say by name at least, or say, gee, whoever thought of this design? Jack, what can you tell us about that?
Well, thank you, John. No one complains about any of the people who contributed to the enormous accomplishment that is the International Space Station. So yes, I'm going to give you a very brief overview of what of my involvement in the program. And soon after joining Anacapa Sciences, a small human factors and applied behavioral sciences research firm, we received a call from Rockwell International, who had built the shuttle and who was serving as the integrator at Kennedy Space Center. It was taking months instead of weeks to refurbish the orbiter between missions, and they wanted to know why. There had been a couple of incidents, including a couple fatalities that occurred on the ground. And I was the new guy at the company, the lowest on the pay scale, and so my boss selected me to accompany him to the Kennedy Space Center, where we spent a couple of weeks interviewing everyone from the director of launch operations to the people who swept the floor of the vehicle assembly building. And when we first met with the director, he said, "Here are your passes and there's your guide. Where do you want to start?" And Doug Harris and I looked at each other and said, "Well, the launch pad, of course." And we then our guide took us to the launch pad. We went up the elevator. Columbia was mated to the solid rocket boosters, ready for the launch of STS-4 in a couple of weeks. At each level, we would pause and look at this magnificent machine. And I actually let our guide and my boss walk ahead of me so that I could literally pinch myself to make sure that this was actually happening. And I decided then that I wanted to remain involved. I'm a relatively patriotic person, but I wasn't just proud to be a member of the society that built such a wonderful machine. I was proud to be a member of the species, and I was so moved by being that close to this marvelous accomplishment. We discovered 22 categories of issues that were impeding the maintenance performance. Little things, some of them pretty large. And when we gave our presentation to Rockwell management at the Downey plant, I happened to notice a sign on a door that said Space Station Working Group. And I thought, well, this might be my ticket to remain involved. And I called around for months trying to find if anybody was interested in the issues of small groups living and working in isolation and confinement. And I would be told, yeah, that's really an important thing. You ought to talk to so-and-so and so. Anyway, I had come to a dead end, and there was a fellow at the Ames Research Center who I had left messages. I didn't get a response, and I was about to give up on a Friday afternoon. I called him about 4:30 in the afternoon, just one last try, and he answered his own telephone. And we chatted for an hour or so, and he said, "Well, why don't you write me a letter about how you would go about studying these issues?" And I spent the weekend writing this letter. And as you know, in all serious fields of inquiry, metaphor is used when we don't have access to the real thing. Engineers and architects build engineering models and then subject them to stresses. Medical researchers use what are called animal models to test therapies for possible human use. Even economists build models to test theories of cost and supply. In the behavioral sciences, we look to analogous conditions. And so I proposed to study conditions on Earth that are characterized by various conditions of isolation and confinement. The folks at Ames invited us to come up and talk to them about it. And then at the end of the day, they said, if you want to write a proposal to do this, we will entertain that proposal. If we don't like it, we'll put it out to competitive bid and you'll have another chance at it. But they liked what I proposed, and I started in 1983 on this study where I looked at identified 12 categories of behavioral issues: hostility of the outside environment, size of the crew, mission preparation, and so forth, and a dozen different examples, from underwater habitats to our previous experiment with the station, Skylab. And that resulted in about 100 design recommendations in 1985. And Gary just gave you a wonderful history of the space station program. And I must say that I learned a lot from that. It was great to see it. But some of my recommendations from 1985 actually made it through all of those design iterations that you just saw to the final design of the International Space Station. The moment of inspiration for me was on the gantry, on the launch pad, I should say, for STS-4. And I had proposed to study conditions on Earth, as I mentioned, analogous to a space station. That report was a big hit with engineers because it was based on real world experiences rather than some psychologist or architect's good idea. Engineers are very, how shall I say, they need evidence. Like, what is the most important issue? And when psychologists would say, well, of course, group interaction, interpersonal relations, engineers would say, great. How do you know that? And what's the second most important issue? And there wasn't really something that could be answered at that time. So the space station study was a hit. And then NASA asked me to do the same thing, but for a 3-year expedition to Mars. And the only analogs to a 3-year expedition to Mars are the expeditions of the past, polar expeditions and voyages of discovery. And I embarked on that study, and what I found was that expeditions and polar winter rover experiences were very similar to the conditions that we might reasonably expect for future space expeditions. Now, I used this picture showing Columbus's 3 ships in I think that's the Banana River, to remind me to tell you that NASA did not invent triple redundancy. It was a common, actually, it was the standard for seafarers in the past, especially explorers. And Columbus never would have departed Spain with fewer than 3 hulls, nor would he have returned safely had he done so. Most people are unaware that the Santa Maria went aground and broke up on Christmas Day, 1492, because they had partied celebrating Christmas the night before and left the watch to a cabin boy. And when a storm came up, he didn't know what to do. And that left Columbus at that time with only 1 ship, because one of his captains had left on his own looking for gold. And it was just an enormous coincidence that captain came back a few weeks after the Santa Maria had gone aground. And they made it back to Spain, and the rest is history, as they say. Next slide, please. My technical report was submitted to the Johnson Space Center, titled "The Modern Explorer's Guide to Long Duration, Isolation, and Confinement: Lessons Learned from Space Analog Experiences," was well received at JSC, but Barbara Wolford, my contract monitor, suggested that I seek a publisher in order to get a wider readership for that material, and I sent it to the Naval Institute Press, and it was published a couple years later as Bold Endeavors: Lessons from Polar and Space Exploration. They humored me about the title for a while and then finally said, no, that was way too long. So essentially what I found was that the details will be different, but most of the problems that will confront the future explorers of space have been confronted already by the explorers of Earth. It won't be outgassing from a gasoline-powered generator that almost kills an astronaut, as it almost killed Admiral Byrd in Antarctica. It'll be outgassing of some other material, but it will be the same sorts of issues. So just as conditions on Earth served as a metaphor or an analog to what we might expect of a space station, the International Space Station, when it became operational in November of the year 2000, it became an analog for future long duration space exploration. And so I proposed to NASA that we could use the astronauts on board as subjects for this analog type, space analog type experiment. And I suggested that if astronauts were to maintain a confidential journal that only they and I would see, I could conduct an analysis of the content in a very systematic fashion in order to derive some, by extrapolation, some guidelines for the design of future missions. So the purpose was to obtain a lot of data and analyze the data in order to come up with some insight. The method that I used was to parse the journal entries into statements, and then a statement could be coded for the category, the primary category, usually a secondary category, and sometimes even three things. People write in often not in the most coherent fashion, and they might discuss three different things in a sentence. Would then code that for the tone, whether it was positive, negative, or neutral, the day of the expedition, and then the role, whether the person was the commander or flight engineer. For example, we were talking about the IP phone at dinner. We, group interaction, that would be category one, we were talking, that's group interaction, about the IP phone. That's the device that's used on the ISS for astronauts to communicate with their friends and family at home. So that's communications is the second. And at dinner, that would be food. So we have group interaction, outside communication, and food. We were talking about it, that would receive a neutral tone. If we were more likely praising the virtues of the IP phone, that would be positive. If we were complaining about it, that would be negative. And so each statement in a journal entry, which could be anywhere from a few sentences to a few pages in length, would get coded in that fashion and pasted into an Excel spreadsheet and used for analysis. The astronauts liked the idea of keeping a journal largely because they wanted to do it anyway. They knew they should probably do it anyway, and this was a good excuse to do it because they would end up with a once in a lifetime, a description of a once in a lifetime for some, and for others, they got to go back, experience. And they liked it because it's the customary method used by explorers of the past and of scientists, engineers, and pilots. And so it resonated with the astronaut corps, and they wrote, everyone who participated in the study wrote candidly. I can't say that they wrote candidly all of the time, but every one of them wrote something that they definitely would not want their management to attribute to them. Next slide, please. So what scientists do largely, if you want to boil it down to the simplest, is we categorize things and then count them. And so first level of analysis for the journals experiment was to count the number of category assignments to, and the categories, by the way, started with a few categories based on a pilot study I had done at French Antarctic locations and tiny islands in the South Indian Ocean. But the categories actually emerged from the data. I didn't make any a priori judgments about categories. And so as you see on the left, phase one, that was the first 10 astronauts. They were members of 2- and 3-person crews, This between 2003 and 2009 or so, not 2010. And the astronauts wrote most about work, followed by outside communications, that is conversations with their family or conversations with mission control and so forth, group interaction, recreation, leisure, equipment. And then in 2010, when the report was published by NASA, it was considered by the astronauts to be very useful because it, and by the Behavioral Health and Performance Directorate. And so they asked me to do this again, another 10 astronauts, because the space station had increased in size and there were now 6 crew members. So it provided a basis for comparison. Now, it's really instructive to look at the categories that are the most important. It's all based, the whole method is based on the assumption that the more someone writes about a topic, the more important it is to them at that time. So it's important to look at the most salient issues, but it's also instructive to look at the issues farther down the list. I expected privacy and personal space to be an issue during phase 1. However, as you can see, it was very low on the list of behavioral issues. And that's largely because with 2 and 3 members of crew members, each person could hang their sleeping bag in a separate module from the bulkhead of a separate module, and often they would go all day without seeing each other, working independently and coming together only at dinner time. So I thought for sure in phase 2 that with 6 crew members that privacy and personal space would be an issue, and as you can see, it was even less of an issue. And that's largely because the station had increased in size along with the size of the crew, but the private sleep chambers had been installed. And there is much to be said for a private sleep chamber when you're confined and isolated with a small group. Each one of the categories was then subjected to a subcategory analysis. For example, these are the data from phase 1 of the work category. And those segments represent each mission divided into quarters. The missions could be anywhere from 5 to 7 months in length, and for each subject, each astronaut, I would divide that person's journal into fourths and then combine the data for the subcategory analysis. And as you can see, teamwork wasn't referenced in their journals that much, lack of teamwork even less. These are 2 and 3 person crews. And with the 6-person crews, there were many more opportunities for teamwork, and so it became more of a salient issue, and lack of teamwork, not so much. I mentioned that each journal statement was coded for positive, negative, or as positive, negative, or neutral, and by dividing the entries, the statements by quarter, and then subtracting the proportion of negative statements from the proportion of positive statements, I could get one metric that can be tracked over time that we called net positivity negativity. And what you're seeing here are for the 10 phase 2 astronauts, all of the statements assigned to the adjustment category, which was closest to what you might call morale or general feeling of the crew, by quarter. You can see that for some, they started off very positive and then kind of went down, and but the bottom line to all of this is that there was evidence of a dip in this net positivity negativity during the 3rd quarters of missions. When combining all categories, 14 of the 20 astronauts showed a decline during the 3rd quarter. When looking just at those statements having to do with adjustment, whether it's physical adjustment or behavioral adjustment, or you might call it psychological adjustment to the conditions, 17 of the 20 astronauts showed a dip during the 3rd quarter. when I first found this this phenomenon in the study that preceded the journal's flight experiment, I thought, wow, maybe I've really hit upon something. And then when it emerged during phase one, I was pretty sure that this was a useful discovery. And then I started thinking about my college days, and we had 10-week quarters. And darn, if that 7th, 8th week, everyone's morale was down because we had so much yet to do and not much time left to do it. I took a road trip with my family when the children were younger, and about 3/4 of the way through that road trip, everyone's morale was down, and yet we all got much more excited as we neared the end. So it might just be a structural phenomenon, something that happens to people when they know about how long some activity is going to last. It might not be limited to isolation and confinement. So all of this is described in excruciating detail in some technical reports, and I would be happy to make those available to anybody if you're interested. Thank you.
Thanks very much, Jack. That's exactly the kind of information I was hoping we're going to get today. I've got a couple of questions for both of you, and then we're going to go to some public questions as much as time will allow. First, getting back to the design for Dr. Kitmacher, I noticed that the spacecraft we saw, especially I think the Russian ones, but some of the earlier American ones as well, look more like the insides of steam tunnels than they do like the sleek, comfortable, spacious Starship Enterprise class starships of Star Trek. Is a spaceship ever going to look commodious and tidy on the inside, do you think?
I think it could be done. It's something that we did worry and discuss quite a bit back during that early design phase. For instance, as we were coming up with the design of the racks of the station, I said to Malcolm Johnson, who was our lead designer in our group, I said, I think these walls are too wide. The astronauts won't be able to even reach them because it's more than 6 feet, and a lot of the astronauts aren't that tall. He said, don't worry about it. There's going to be so much stuff in here. It'll be very easily for them to grab onto things. And in the end, right now, the way ISS is, there is a lot of stuff. Now, keep in mind, we had originally the idea that we were going to have storage modules and logistics modules that the astronauts would be working out of to take equipment and then putting used equipment or garbage back into. And early on, those were eliminated. Eventually, they did bring one of those logistics modules back. Now they do have some of the unmanned spacecraft that kind of support that kind of ability. They have the beam, the inflatable module that is used in that form. So depending on how much space there is to put things away and on a place, I think that it can be made much nicer. If you looked back at the Mir or at the Salutes, they were very tiny spaces. They were not optimized at all for any kind of storage. So they were exactly that kind of a steam tunnel. It was a concern. I remember Carolyn Huntoon, when we first talked about the nodes of the space station, that those are going to be boiler rooms. There's going to be so much equipment, the astronauts won't even want to go in there. And sure enough, we have modules of the space station that are nodes. So
good. Well, hopefully we can strive for more commodiousness in the future. Jack, let me ask you a quick question about that third quarter phenomenon, the dip in the third quarter in the NPN index. Is it bad? And if so, what can be done? What do you think can be done to mitigate it? Is it bad to have a bit of a dip as you see the end coming up ahead of you, but still far away? And do you think it'll affect performance? And if so, what might one do? Not tell the crew when the mission's going to end so they don't know when the third quarter is?
Oh no, that would be even worse. Um, for many, the dip is minuscule. It's not even detected by the mood scales and other typical tools used by psychologists to measure affect or morale. For many, it's minor. Some astronauts start off very positive, and everything just gets better and better and better. But others are more human-like and are subjected to the same sort respond differently to the stresses. My recommendation was to schedule more of the crew discretionary events during the third period. Those are events. Al Holland runs an office at JSC dedicated to providing psychological support to the crew and their families. And astronauts are offered the opportunity to select an individual who they would like to talk to, who they under normal circumstances probably would never get to talk to. And so some astronauts want to talk to a musician, a favorite musician. Others want to talk to an author or a fellow scientist, and some select an actor. And I think one of the most often selected is William Shatner, and astronauts have described how much they enjoyed talking to the most famous starship commander of all time and having him ask them what it's like to be in space. So those crew discretionary events are very helpful, and that Al Holland's office does a wonderful job providing that kind of support. If I could go back to something that Gary said about translating or moving through a module and touching objects along the way in order to get to propel oneself in this simulated sort of weightless environment. During Expedition 8, there's a Russian and an American crew member. Their mission control detected a leak. It wasn't a real dangerous leak, but it had to be addressed. That is, leaking the atmosphere inside the station to the outside, and it had to be addressed. And so, for a couple days, the crew wandered through the station system. Not wandered. They progressed through the station with an ultrasonic wand looking for the source of the leak, and it couldn't be found. There was a slight blip as they passed by that window that Gary showed. And if you recall, there was a little tube leading from that window. And it was getting very serious, and the Russian program and the American program were contemplating shutting down each module one at a time, trying to isolate the source, which was going to be very disruptive. And so hanging in his sleeping bag one night, Michael Foale was thinking, what could it possibly be? And he thought back to that blip they noticed as he passed by the window. So he got up in the middle of the night. Now, the night is an odd concept when you orbit the Earth every 90 minutes, but it was the middle of his sleep period, we'll say, and he retrieved that device and floated over to the window, and there was nothing. The needle didn't jump at all. And then he thought, well, what is it that we do here at the window? And he says, well, we hang on to look out, and as soon as he touched that little tube, the needle spiked, and he let go, and the needle went back, and he touched it again, and what they found was they were using a tube that was designed to vent between the two panes of glass, and that when they, over time, had been touching it through the 8th expedition to the ISS, crews had been, and visiting shuttle crews, everybody wants to look out the window, and so that tube had become slightly dislodged. And for the longest time, anyway, so they were able to fix it. But for the longest time, I thought that whoever designed that, violated the first rule of human factors design, and that is don't make something look like a handle if you don't want people to use it as a handle. I later learned that that window was supposed to be covered by another structure that had handholds on it and camera mounts and was perfectly designed, but that device, that covering, didn't get installed until about the time that the cupola was installed. And I imagine people still look out that Harmony, or was it Harmony window? Destiny window. But the cupola is now the most favorite place for Earth viewing.
Yeah, Jack, I heard that they actually put a placard there saying, "Do not hold on to this fixture."
Well, that would have
solved
helped
the problem, I'm sure.
Yeah, I'm sorry to digress, but I couldn't.
No, it's not a digression. Actually, that's my next question for both of you. One of the questions we got from our audience, from Bernie Thomas, and he asked a question relating to the windows. Dr. Kitmacher, you showed us sort of the evolution of windows over the course of the station, and in fact, your own work with the cupola as I think a real milestone. And considering what Dr. Stuster just told us about the window and the module, Bernie's question is, how is it possible to stop staring at the Earth? I would never want to be pulled away from the observation window. Either of you have any insights from astronauts about how hard it is to peel your nose away from those windows and get back to work?
Well, it is the favorite in the journal's experiment. Recreation and leisure is the most positive overall category, and the number one leisure activity is Earth viewing and Earth photography, and it also contributes to sleep problems during the early parts of each expedition, because the astronauts have trouble pulling away from that wonderful view, and they stay up later and later at night, and then it makes it more difficult to get up in the morning. But they eventually learn to budget their time. But even during the middle of the day, if their activity involves them passing by the cupola, they grab little snippets of that wonderful recreational and leisure activity of looking at Earth. Gary?
I know some of the astronauts have actually slept in the cupola or slept near the cupola, so that they're close to the window and they can look out pretty much anytime they want. So I think the viewer is probably right. The astronauts do enjoy doing it, and it offers them a viewing opportunity, an observation capability that they aren't going to have anyplace else. I've heard that the only place better is if you're out on a spacewalk and your head is in the fishbowl of the helmet. But otherwise, the cupola, because it surrounds you basically 180 degrees, you get a very wide vista kind of a view. You can really relate to that.
Let me ask one more question for both of you. These are actually a combined set of questions from two of our audience members, Mark Berglund and Ken Johnson. I'll combine the questions. How aware is the crew of what's happening back here? Can they see, detect signs of changes in human activity, and can they see less pollution right now? I think right about now during our COVID-19 self-quarantines, there's a discussion about less pollution worldwide. But have either of you come across discussions from astronauts about how aware they are of life back on the Earth, and including things like pollution?
Yes. And by the way, if you want to find some of their observations, you might go to the oral history website for the either for the Johnson Space Center, or I think some of the other space centers have them as well. But the astronauts in particular have often been interviewed for the history office, and they have said, especially the ones who have flown multiple times over many years, John Young comes to mind, for instance, who first flew back in '65 on Gemini, and flew a total, I think, of 6 or 7 times all the way up through the 1980s, that he could see distinct changes in the Earth and the atmosphere over that period of time. And the astronauts can actually look down and, depending on their eyesight or whether you're using binoculars or telephoto lenses on their cameras, they can see signs of life on the Earth. There's no doubt about
it. It's fairly well documented that many astronauts, if not most astronauts, are forever changed by their experience in space. Many have written about watching the Earth pass beneath them and not seeing evidence of borders, and which contributes to a different perspective on society. They also report that looking at Earth obliquely and seeing how thin our atmosphere is clinging to this planet, that they develop an appreciation for the environment as well. And many have come back, and when they retired from the astronaut corps, become active in environmental issues. You mentioned the perhaps effects visible from space of the quarantine efforts on Earth. And I just wanted to mention that there is much that we can learn from the astronauts' experience that can be applied on Earth, from a enhanced appreciation of the environment, an enhanced notion of cooperation, and that we are all in this together, that might be useful for the future. And even in more instrumental ways, we can learn how to endure our confinement during the pandemic, how we can endure this period, by learning from how the astronauts have done so. And if I can just offer a couple suggestions, if one could, the astronauts generally, before they launch to orbit, set as their number one goal getting along with their crewmates. And they also work to a schedule. And it's okay to sleep in on a weekend on the ISS, and it's okay for people in confinement on Earth to sleep in, but it's important that you also have a schedule. It's very important to eat meals together, at least one meal a day, which applies to crews in orbit, and it applies to families or roommate situations on Earth. Eating together fosters solidarity, and it helps break down those barriers that normally develop among groups or subgroups. It's important to conduct group leisure activities. The astronauts, it used to be more than it is now, but when there were 2 and 3 crew members, they would eat together every evening, and they would every weekend would be a movie night. It's less so now, but at least on the weekends, the astronauts and the cosmonauts, everybody gets together for a meal and either watching a sporting event or a movie together. There are great pictures of the crew watching, say, The Martian the day before it was released on Earth. Anyway, but for individuals to be polite and respectful, to avoid derisive humor, the kinds of humor that puts somebody down, to do more than your share of communal tasks, to consider the possible consequences before you say or do something, to consciously attempt to be cheerful and supportive, to be considerate, and more than that, to avoid being annoying in any way. And there are lots of guidelines derived from the space analog research and from the astronauts' experience on ISS that we can employ here on Earth. And, as as Fridtjof Nansen once wrote, we are all explorers, really, each one of us seeking his or her own path through life. And I think we can benefit from that kind of perspective.
Well, Jack, thanks very much, Dr. Stuster. That's excellent final words for this spectacular session. I cannot imagine having a better session with more relevant discussants than you two gentlemen. And I am chastened that some of the advice that astronauts give to everybody else is, number one, don't be annoying. I have to work on that, I guess. But let's assume we all have some personal goals yet to attack as we have the opportunity. I'd like to thank both Dr. Stuster and Dr. Kitmacher for being our guests today on this Thought Leader Series presentation. I think your presentations have demonstrated ample evidence of human presence on the International Space Station from the get-go and all the way through today. So with that, thanks very much for your participation, and thank you to William for letting me host this session this afternoon. Thanks very much.
Great, thank you, John. What an incredible panel, hearing about the history and the relevance to today. I love that point as well about not being annoying. I'm going to really strive toward that as well, given the challenging times we find ourselves in with the pandemic. Well, that brings our program to conclusion. I want to remind everyone that this episode will be archived on our website, www.spacecenter.org, where you can find all kinds of great information on our digital platform. Given the times, we've actually added our programming. We have a new experience called History Up Close, where you can actually look at many of the incredible artifacts we have at Space Center Houston up close. We actually have virtual tours available through our app if you download that. And we're also doing a whole series of programming in celebration of 20 years of continual human habitation on the International Space Station. And of course, we're entering the week of the 50th anniversary of Apollo 13. And Space Center Houston is going to be rolling out all kinds of great programming. We will have activities available online recognizing this amazing anniversary and incredible achievements of the flight controller and astronauts to bring the crew back safely. And we'll have other celebrations as the year progresses. So thank you so much for joining us today, and join us for our future Thought Leader programs. Thank you. Goodbye.